Hello everyone, welcome to today's class. Today we will discuss about the topic of combination of thin lenses. Under this topic we will discuss that why the combination of thin lenses is of an advantageous situation and how their focal lengths are related to each other. We will also discuss how this combination of thin lenses is important to use. So let us start. What is combination of lenses? So when two or more than two lenses, whenever they are placed in contact with each other or close to each other with some distance between them, we call it to be the combination of the lenses. And this combination produces an effect which is equivalent to some single lens whose focal length is same as the focal length of this combined, we can say combination of the lenses, right? So together the lenses give rise to a effect of a single lens which has the focal length which is given by these two focal length of these two lenses. So here are the two diagrams of using the combination of the lenses. In the first diagram, the lenses are placed with contact with each other, right? In other case, there is some separation between the lenses. So there are the two ways in which the lenses can be used. So whenever lenses are used, for example, in front of this lens, we have lens L1 and L2, and in front of this lens L1 we have an object on the principal axis. We always place the lenses such that their principal axis is common, so that their optical center are on the common principal axis. So such a kind of combination is of very important use. So what happens here? Here suppose that we have an object on the principal axis. So its image, if there was no second lens, then its image would have been formed at position I1. But because there is another lens of similar kind here, for example, which is also convex, L2 lens, so it makes the light ray to converge even more and bends the light ray towards the principal axis with a greater extent, so that the final image is formed at a closer distance, right? So we see that whenever this object lies on the principal axis, it sends the light rays on the lens L1, which should have been converged at position I1 on the principal axis, but because it is the second lens which is placed in contact with the first lens, so it makes the light rays to converge even more and make the image, final image, at a closer distance I, or at a closer point I. Now this I1, this point will act as the virtual position of the object for lens L2, for which the lens L2 is making the image at position I. So I1 will behave as a virtual object, or we can say if in actual practice the object is lying at I1, then its image will be formed at I. So this is how this lens combination takes place, and so is the case with the second combination. The only difference is that what this distance between the lenses plays role here. We will discuss them in the coming steps. So what use of lens combinations makes for us? The lens combinations are used for various purposes. Number one, combination of lenses or lenses in combination, it increases the magnification of the image. That means we get a larger size of the image whenever we combine the lenses. In place of using single lens, for example, if we make use of two lenses, the image will be even larger in the size. So that is the one application or use of combination of the lenses, that the combination of the lenses increase the magnification of the image. Another use is that it produces an erect image if the final image produced by a single lens is inverted. Suppose that convex lens is there, right? So in all cases except one, it forms the inverted image, so that becomes difficult to visualize, or if we want it to be the erect, we can make use of the combination of the lenses, because the image formed by the first lens, it will be inverted, right? This inverted image, it will behave as an object for the second lens which is placed in combination with the first lens, So now the second lens will also invert the inverted image so as to make the image erect, right? So in this way, by using the combination of the lenses, we can get an erect image. Another advantage of using lens combination is that it minimizes spherical aberrations. Spherical aberrations are the problems which arise due to the aperture of the large lenses. Suppose that for the purpose of, for example, telescopes, we need the lenses of large aperture. So there comes that the thickness of the lenses changes appreciably from optical center to the edges. So in that case, the errors arise in the image are called as the spherical aberrations of the lenses. So by making use of combination of the lenses, we can reduce the spherical aberration which happens in the lenses. We will discuss this a little later. And one more advantage is that it increases the field of view. By using two lenses, now these two lenses can gather the light from a wider view of the field, right? So these are some applications or uses or importance advantages of using the lens combinations. Now we can discuss how the focal lengths of the two lenses which are combined together are related to each other and how they give rise to a new focal length which is equivalent to some lens which produce the same effect, right? Suppose that we have two lenses, we are taking the same diagram for which the object is O. Its virtual image is formed by lens L1, virtual because it is the second lens which is placed in contact with the first lens. So the first image found by lens L1, it would have been formed at position I1. Now because there is second lens in combination with the first one and in contact with the first one, so therefore the final image is formed even at a closer point I, right? So we can write the two lens equations for lens L1 and for lens L2. For lens L1, the image is formed at I1, right? So we write the equation, lens equation for it as this. Lens equation, let me recall it, it is nothing but the relationship between the object distance, image distance and focal length of the lens. So here V1, we are taking the distance of this point I1 from the lens L1 as V1. So it is V1 minus 1 upon U, which is equal to 1 upon F1, where F1 is the focal length of the first lens and F2 is focal length of the second lens, right? So this is the lens equation for the first lens. Now there comes second lens. For second lens, the object it is placed virtually at position I1. So therefore the distance of this object from this lens L2, it will be V1, right? So the object distance is V1 and image is formed at I, so its distance is taken as V from the lens L2, right? Which is equal to 1 upon F2. So this is how we write the lens equation for the second lens. For the second lens, the object is placed virtually at position I1, so whose distance is taken as again V1 because we are using two thin lenses placed in contact with each other, right? Okay, so these two lenses will now behave as a single lens whose focal length is given by, for example, this F, capital F or even a small f, right? So we see that for this combination of the lenses, object is placed at distance U and image is formed at distance V, and the combination of the lenses produce one single lens whose focal length, let us take it to be F. So we can write the lens equation for this combination now together, right? Or we can say for one lens which produce the same effect, which will produce the image of the same object at position I, if that lens is also placed at the position of these two thin lenses. So therefore from equation numbers 3 and 4, from these two, now what is this equation? This is nothing but the sum of these two equations, number 1 and equation number 2. So on the left hand side, this term just cancels out, 1 upon v1 minus 1 upon v1, it just cancels out. Only the thing is left, 1 upon v minus 1 upon u, which is equal to 1 upon f1 plus 1 upon f2. And by using the generalized result for the combination of the lenses, or we can say for the one single lens, which will produce the same effect as produced by these two lenses together. So from equation number 3 and 4, we see that this left hand side, 1 upon v minus 1 upon u, it is nothing but 1 upon f, the focal length of this combination. So we get the focal length of the combination to be the rest 1 upon f1 plus 1 upon f2. So this is the relationship to find out the focal length of the equivalent lens. So these two lenses together, placed in contact with each other, they will produce the effect of one single lens whose focal length is given by this equation. On the other hand, if the lenses are placed at a distance x from each other, then again their combination will produce one single lens whose focal length is given by this formula or this equation. So f is the equivalent focal length, or we can say focal length of the equivalent lens. So it is given by 1 upon f is equal to 1 upon f1 plus 1 upon f2 minus x, where x is the distance between these two thin lenses. In some books it is taken as small d, so whatever the notation is, it does not matter. It is just the separation between the lenses divided by f1 into f2. So if the lenses are at a distance from each other, then they will produce a lens, or we can say effect of an equivalent lens whose focal length is given by this equation, or can be calculated by this equation. So this is everything about combination of the lenses. You must practice the questions based on the combination of the lenses. They may be the lenses of similar kind or different kind. There may be the lenses of these two lenses we have taken are the convex lenses. There can be the combination of the concave lenses, or the combination of convex and concave together. So we have to just use their focal length according to the sign convention and make the calculation. Now we can proceed to the next important article, which is on prism. So very first thing here to understand is that what a prism is. So a prism is nothing but a transparent refracting medium which is enclosed by two triangular sides, or we can say surfaces, and three rectangular surfaces. So let me just mention it once again. A prism is nothing but a transparent medium which is enclosed by two triangular surfaces and three rectangular surfaces. So whatever shape of that transparent medium we get, it is called as the prism. So in general, in laboratories we have glass prisms or hollow prisms, in which we can fill out any transparent liquid for which we are willing to find out the refractive index. So under this topic we will discuss that how light rays get refracted whenever it is allowed to pass through a prism, and there we get a very important result called as the Prism formula, and then from that formula we will discuss about finding the refractive index of the material of this prism, and then on the basis of this prism we will understand the dispersion phenomena of the constituent light or a composite light. So let us begin with the prism formula. So here for symbolic purpose we make use of this diagram. So we have to incident the light ray on the rectangular surfaces. So the light ray which will come out of the prism, it will be out of another rectangular surface. So we will observe all this situation from the top. From the top means from the triangular face of the prism, right? So for this we are taking this to be the point A, it is B, it is C. So we are looking at the prism from the front section, right? So it is a prism. In laboratories we have prism of equilateral sides, in which all the three angles of the triangular surfaces are 60 degree each. So this angle A, it is called as the angle of prism, and BC, it is called as the base of the prism. If the light ray is incident on the face AB and it comes out of the face AC, then A it is called as angle of prism, and BC it is called as the base of the prism. So this light ray which is incident on this surface AB, it just at this surface, it just finds the medium which is different from the earlier one. Earlier it was traveling in air, for example, and now it is traveling in glass. So therefore the light rays changes, the properties of the light ray changes, and hence in order to compensate that change in properties of the light, just like speed, wavelength, it just changes its direction. Because it is coming from rarer medium to denser medium, so the light ray bends towards the normal. So here it is normal. N1O, it is nothing but the normal at this point P on this surface AB. So this light ray now travels in the glass medium along PQ. So PQ is the refracted light ray. Again at surface AC, the light ray again finds the medium changed. Now it is emerging in the same air medium. So therefore light ray bend away from the normal now and move along this path. So this is how refraction of the light takes place whenever it is passed through a prism. This you have already understood in case of your class 10th during your refraction through the prism topic. Now here it is the second normal N2O, which is at point Q on the second surface. So this is the first surface of the prism at which the first refraction takes place, and this is the second surface of the prism at which second refraction takes place. So light ray follows or undergoes two refractions, or we can say refraction at the two surfaces whenever it passes through a prism. Let us make some notations here. Here it is nothing but angle of incidence. This is angle of refraction R1 at first surface AB, and this will be angle of incident at second surface, and this will be the angle of refraction at the second surface. It is called as angle of emergence because light ray is now emerging to the same medium from which it was coming. So that's why it is represented by E, angle of emergence. So initially the light ray was traveling along this direction, and finally the prism has made the path of the light along this direction. So there is an angle represented by delta between the original path of the light ray and final path of the light ray. So this angle delta, it is called as the angle of deviation. So prism has deviated the path of the light ray by an angle delta. So this is called as delta. So all notations are self-explanatory. Let us proceed for the derivation of the formula. So for this we take the use of this first shape A, P, O, Q. This is nothing but a shape which is enclosed by four sides. It is a quadrilateral in which these two sides, PO side and OQ side, these are at right angles. So these are the two right angles. So that means their opposite angle, the sum of other two angles will also be 180 degree, because these two angles, angle P and angle Q in this quadrilateral, forget everything, remember this quadrilateral, angle P and angle Q are 90 degree each, so their sum will be 180 degree. So that means the sum of other two angles will also be 180 degree. So in this quadrilateral A, P, O, Q, angle A and angle Q together they are 180 degree. This is because N1 and N2 are normal. So these two sides are at right angle to the side AP and AQ. And also in triangle OPQ, this is triangle OPQ. In this triangle, the sum of all the three angles will be 0. So this angle O plus angle this, which is R1, plus this angle R2, all together will be equal to 180 degree. Now if we compare these two equations carefully, we see that this angle A, it will be equivalent to R1 plus R2. Only then whenever added to angle O, it will be equal to 180 degree here in equation number 1 and in equation number 2. So that means A, it is equal to R1 plus R2. So from 1 and 2 we see that that means angle A, it is equal to angle R1 plus angle R2. And also in the triangle DPQ, so this is point of deviation, it is DPQ in this triangle, right? Angle delta, it is the exterior angle. For the triangle DPQ, angle delta is the exterior angle, which will be equal to the sum of two opposite interior angles. So what are interior angles here are, it is DPQ and DQP. So how many are these exterior angles? Oh, sorry, into interior angles. What is their value? So DPQ, it, because it is this angle is I, so this angle DPO, it will also be equal to I, out of which this is R1. So that means remaining angle DPQ, it is equal to I minus R1. Similarly here, this angle DQP, it will be equal to angle, this will be equal to E, out of which it is R2. So angle DQP, it will be equal to angle E minus angle R2. So this is how we have written this exterior angle property here. Now we are just rearranging these. I plus E are put together and R1 and R2 are put together. So it is R1 plus R2, and from this combination, or we can say these two equations, we already know that A, it is equal to R1 plus R2. So that means in place of R1 plus R2, we can substitute the value A. So that's why this equation number 3, it becomes delta, the angle of deviation, it is given by I plus E minus A. Or let us rearrange it in order to get this equation, right? I plus E, it is equal to A plus delta. So this formula, it is called as the Prism formula. It relates, it is the relationship between angle of incidence, angle of emergence, angle of prism and angle of deviation. This is the first part of this class. Please refer to the second part for the next class and the remaining topic of this topic on prism.